So here we have two functions. I am going to color code them. I'm going to color code g of x. I'm going to put it in blue, f of x in green. So in part A, when we want to do the domain of f of x, first of all, what kind of graph will that be? It's just a straight line. Domain of a straight line, everything. Range of a straight line, everything. G of x, absolute value of x. Domain of that, if you think about the graph, it was one of our parent graphs way back from our transformations unit, the very first unit that we had. Domain is everything. The range, bigger than or equal to 0. Now off to the side here, I'm going to graph both of those, just so that we can see what the graphs look like. F of x equals x plus 2 would have a y-intercept of 2, a slope of 1, would look like this. And our blue graph, the absolute value of graph, would look like that. So if h of x is adding those together, and another important definition to highlight here says write the explicit equation. An explicit equation is when you're not using function notation. You're just using x's. So h of x is equal to f of x plus g of x. This is not an explicit equation because it has functions in there. But we can change it into an explicit equation. Instead of f of x, I could write x plus 2. Put it in brackets even. And instead of g of x, I could just write the absolute value of x. And that would be an explicit equation for h of x. Now, if we look at our graph and we add things together, we could take certain points, right? Here it's 0. What's 0 plus 2 if I add them together? I'd get 2. Here I would have 1 plus 3. What would I get? 4. Looks like I'd have 2 plus 4, 6. And so on and so on. What's going to happen here? 1 plus 1, 2. 0 plus 2, 2. Negative 1 plus 3, 2. Kind of weird looking. Okay? What ends up happening here is it ends up being a straight line because everything cancels each other out. And what happens here is we get a line going up like that. Now I'm going to show you algebraically how you could figure that out. Okay? Because in B it says once you've done it, can you write the domain and range of that red graph? Well, now that we've got a graph, we can see that our domain is still everything, and our range now is y is bigger than or equal to 2. But you might feel like, ooh, first of all, that straight line across should feel a little awkward. And you might feel like, well, how do I know that it didn't dip down lower or something else happened in between there? How could I figure that out? Well, we're going to look at it algebraically. And often for the range part of these questions, when you get into the homework, you're going to have to use your graphing calculator and try to look at the graph on your graphing calculator and estimate as best as possible. And sometimes even that won't be super good. For this one, I'm going to show you something algebraically you could do with this one. Looking forward to the final exam, you probably won't get complicated algebraic ones on your final exam. They'll probably both be polynomials, which you could add really easily, not a polynomial plus sign or a polynomial plus an absolute value like this one. But I like this one because it teaches us something I think that's interesting. First of all, can you see that your absolute value graph, which is the v, is really just two lines put together? This side's line is just y equals x, and this half is y equals negative x. In fact, sometimes the absolute value of x is written like this. It's equal to x, which is this half of the line to the right, when x is bigger than or equal to 0. And it's equal to negative x when x is less than 0. When something is written this way in two different pieces, it's called a piecewise function, because you don't write it all together as one function. It's written in two different pieces. Now, if we think of this written in two different pieces, we could say, well, h of x, which was equal to x plus 2 plus the absolute value of x, could be written in two different pieces as well. Can you see that if you decided to only use when x is bigger than 0? When x is bigger than 0, then the absolute value of x is just x. And if I simplified, what is x plus 2 plus x? Does that make sense when x is bigger than 0? That this part right here would just be an x. And if I get x plus 2 plus x, I would get 2x plus 2. Now, when x is less than 0, then this part would be negative x. And x plus 2 plus a negative x would just be 2. So now if I scroll up and look at the two pieces of my red graph, does it look like I have 2x plus 2 when x is bigger than 0? Does it look like I just have the horizontal line at 2 when x is less than 0? So this would be algebraically how you could come up with that. Again, you're not going to be asked to work with piecewise functions on your final exam, and I don't think you would get a range question dealing with this. In this chapter, the focus will be on the domain parts, because the range parts, especially in this one, looking at your original green and blue graph, did you expect the red graph? No. And so it is difficult to see the range and all the intricacies that could happen, especially when we get into the multiplying and dividing stuff. So for part C says multiply them together. So part C, p of x would equal this one times by this one. And if you wanted to, we could write this as a piecewise function. When x is bigger than or equal to 0, then the absolute value of x is just x, and x times x plus 2 would be x squared plus 2x. And when x is less than 0, the absolute value of x would be negative x, and negative x times this would be negative x squared minus 2x. So I'm going to show you again, this is beyond sort of the scope of this course. You're not going to be tested on this, quizzed on this, but it is interesting from a math perspective. Maybe I'm the only one who finds it interesting, but that doesn't matter. I'll do it anyways. So if I wanted to graph p of x, I can't graph this easily. I could type it into my graphing calculator and see what it looks like, and from there I could get my domain and my range. looking at it, you should be able to say the domain is everything. You wouldn't need your graphing calculator for that. Because are there any non-permissible values? No. So since there's nothing you're not allowed to put in, everything would be allowed to put in to that equation, and the domain would be everything. But when we go to graph this, we're going to need to use this piecewise function in order to graph it. So what I'm going to do, again, I'm going to use different colors here. I'm going to graph y equals x squared plus 2x in blue. I'm going to graph y equals negative x squared minus 2x in green. And I'm going to graph the actual graph of p of x when it's put together in red. In fact, I'm going to graph the blue one just with a dotted line and the green one just with a dotted line first. First of all, in order to graph these are both parabolas. I am going to complete the square. Remember the completing the square so that I get the vertex form so we can graph it quickly. What would I need to add in here? Plus 1. If I added 1 in there, I would have to minus 1 there. And this is x plus 1 squared minus 1. Same thing on the other one. I would first factor out the negative, leave a space there. What would be in the first place? Plus 1. What would be in the second one? Also a plus 1, because this minus would hit that 1, meaning we've subtracted 1. So in order to compensate, we add 1. So our final equation for this one will be negative x plus 1 squared plus 1. Graphically, what does this mean? For the blue graph, I would have a vertex at negative 1, negative 1. It opens up. I could go over 1, up 1, over 1, up 3. And like I said before, I'm just going to draw this in a dotted line to start off with. My green graph, where is its vertex? Minus 1, plus 1. It opens down. Over 1, down 1. Over 1, down 3. That's my green graph. Now to graph p of x, I need both of those. But p of x, when written this way as a piecewise function, has two pieces. It uses this piece when x is bigger than or equal to 0. X squared plus 2x, that was our blue graph. And negative x squared minus 2x was our green graph. So for p of x, we need the blue graph, but only when x is bigger than or equal to 0. So if I go to my graph and I look at my blue graph, that's the only section where it's bigger than or equal to 0 for the x values. And then for my green graph, it says I should use my green graph when x is less than 0. And so your red graph, it kind of looks like an x cubed graph, but it has a sharp point right there. So it's kind of weird looking. But now that I've graphed it, again, we said already that the domain, you could tell just by looking at the explicit equation that it should be XER, should be everything. But now that we've graphed it, we can see that the range is also everything. Okay, questions you can do for practice? 3, 5, and 10. I'll leave this up here.